So now we will learn about entropy. So as we mentioned before, let's go back to the simple situation again. So there is number between 1 and n, and Alice chose x, and Bob wants to guess. Bob asks some yes/no question to determine x, and we want to measure the amount of information that Bob gets from each question. Here, the amount of information can be considered as how much can you shrink the candidate. It's a one interpretation. There are several interpretations of entropy. You can consider it as the amount of information or amount of surprise, or in discrete way, in this specific situation, you can consider how much, you can shrink the probability space. So, you can kind of consider, this, so that each of Bob's question give you 1 bit of information. Here, 1 bit is the ability to shrink the probability space into half, 2 to the n possible candidates for the answer. But after one question, it shrinks to the 2 to the n minus 1. So this shrinking ratio is 2. And in order to deal with it in additive sense, you take the log. So log shrinking factor, and you want to make it positive. So minus log half. And let's change the setup slightly. So we consider, so instead of this discrete set, we consider a uniform probability distribution. On this 2 to the n bracket set. Or equivalently, you consider a random variable which is chosen from this set in a uniform way. So these two are equivalent concepts. You have a probability distribution on there, or you consider this random variable which has that probability distribution. So they are essentially the same object. And we consider the random variable y1 to say yn, which may depend on x. So we don't say these and these are independent. They don't have to be independent. Each of the random variable may be dependent on x. So you can consider each of these as an answer to Bob's question. So it's either say yes or no. You can consider indicate the random variable 0 or 1 depending the answer of the Bob's question. And if after n question Bob can determine the x, that means y1 to yn actually carries the full information on x. So it carries enough information to determine x. Then now we can ask what n can be. So this n and this n are same, so let's say t. Then it's easy to actually, discretely we can easily check that you need at least n answer. But we want to somehow, want to measure the information that each of these random variable carries, and this random variable carries. And then if we can measure them, then information that these all together carries must be at least as large as the information of, this one carries. So that motivates the definition of entropy. So before we define for a given real number p, we define this. But more generally, we want to define the entropy on a given random variable. Let's say discrete random variable. Again, let's say y is discrete random variable. Taking values in some S, set S. Then, by the same, we can consider that there is event X in S. With the probability, say P. Let's say this is a discrete event. So if in Y, if we know that its value is X, so you can imagine that these are like each of these are like asking the ith digit in the binary expansion of X. So it's either 0 or 1, and once this is 0 or 1, in the total total probability space, how much it shrink? That's same as this situation. You can consider this as 0, 1, and this is 0 or 1, depending on this y. And then once this happens, which has probability p, this has probability p means that the entire probability distribution, the probability space, shrink by p. In this above example, we know that x could be any element in 2 to the n bracket. But if you know that the first digit in binary expansion is 1, then there are half of them only possibility, half of the possibility is gone and half of the possibility is left. So this is same as getting negative logs up to p bits of information, which is that the total probability space shrink into a smaller one by this part is, we know that it didn't happen, so that's roughly what we can consider. And we can consider again the expected amount of information. That's our motivation of defining this entropy. So we consider all the discrete events which has probability PS. And this is the amount of information, let's say H of SB, P, minus log probability of S. This is summation of minus PS log 2 PS, where we write PS for the probability that the event S happened. Let's say Y is the random variable we took, so Y. So in the above situation, if we know Y1 to Yt carries enough information to determine X. If that's the situation, then the expected amount of information that these carries must be at least the expected information that X carries. So we can roughly write in this way. So we didn't really define what this means, and we didn't really discuss why we can write this way, but we will see later. But if we can write it in this way, then in the above example, we can actually, consider the entropy. Then this is log sub 2 to the n, which is n. You can compute it. So there are like 2 to the n probability times log 1 over 2 to the n for all 2 to the n cases. Then you actually get this number. And each of the question, if we know that each of x, y, I is at most 1, because, okay, we didn't really show it yet, but if we can show this, then this is at most t, so we can get the n and t. The t has to be at least n. So this is something that we want to do. So for this, there are several things we have to do. First is that we have to be able to say, this h of yi is at most 1. In other words, yi is taking values from 0 or 1. And we know that if yi is uniform, let's say some random variable is uniform in 0, 1, then we know that its entropy, you just compute it, is minus half times log half minus half times log half, which is exactly, because log is base 2, which is exactly 1. So first thing we want to do is that we don't know what this random variable is. It could be non-uniform. But we want to show that no matter what it is, it has a smaller entropy, smaller than equal entropy than uniform one. So you want to kind of compare this with the uniform random variables entropy. Because in the end, what we want to do using this entropy is we want to kind of count the discrete object. Because we are doing combinatorics, we want to count the discrete object. But counting is kind of same with computing entropy when uniform measure is given. When uniform measure is given and you know that the number of pieces exactly, then you can actually compute the entropy exactly. And if you know the entropy, and then if you know this is uniform, then you can actually use it to count the number of discrete objects. So this motivates that we want to compare arbitrary random variables, entropy of arbitrary random variable with the entropy of uniform one. And we want to, next thing is that we want to, kind of add information. Or equivalently, we want to measure partial information. What it means is that here we want to kind of, let's assume that there is y1 and y2, and we have a probability distribution. And y and y2 gives us a partial information about this probability distribution. For example, if this x is in 2 to the n, and y1 tells us the, in binary expansion of x. y1 tells about the ith digit, and y2 1st digit, and y2 tells about the 2nd digit. Then these two give the independent information. The first one, knowing first one, cuts down the probability space to half, and whatever the first one was, second one again cuts it down to half. So it's kind of independent. But if, this tells about the first digit, and if this one says that, say, some other information, let's say, is x congruent to 1 mod 4. If this is the second question and you get the x yes and no, then this could be not really independent from the previous answer. If the previous digit was 0, then the second question does not shrink the probability space further. So what I want to say is that there are some random variable. If they are not independent, then the information that this carries, and then later this gives us further information, but some part of this further information was already given. That could be possible. So this carries 1 bit information, this carries, say, 1 bit information, but they together could carry less than 2 bits information. So in order to add the information that we want to get, we want to also measure the common information, the partial information which was get from the previous one. Measure, say, common information. So that's another thing that we want to do. So we need to come up with these two, and then also we need to be able to compare certain amount of information. In certain situation, this random variable must have carry more information than the other. For example, if we have two random variables y1 and y2, then it might not carry too much information, but it's at least carrying more information than y1 alone. That's that's quite intuitive. So we want to prove such, several inequality. So our goal is that we want to compare the entropy of normal random variable with a uniform one. And we want to be able to add the, entropies, add the information that we get from several random variable. And somehow while doing that, we want to be able to measure the common information. So that's what we want to do. So in next video, we will prove several facts about this entropy. And probably we will be able to do, run some application in the next time, probably.